who I will introduce. We have a guest speaker today, Junjie Hu, who I will introduce in a moment. We have one announcement, or rather one clarification to make, which is it's important that you know that the exam that will be held on the last day of class, rather than a final exam in the classical sense, is more of a second midterm. So it will cover only material from the middle of the semester forward. That is, it will not cover any of the material that was covered by the previous midterm. So just so you can focus your studying and not feel too stressed out, we wanted to let you know that. Anyway, with no further ado, I would like to introduce our speaker for today. That is Junjie Hu, who is a PhD student in the LTI and is an expert, among other things, on machine translation. He just got, he's famous now because of his work with some people at Google DeepMind. That's right? Google DeepMind?
Yes, we have a
Anyway,
work.
yeah, so on some things that are not just machine translation, but so he does other things too, and he's a very smart guy, so listen to him. So let's give a big welcome to Junjie.
Yeah, thanks, David, for the warm introduction. So let me share my screen to present. So can everyone see my screen here? Okay, so today I'm going to briefly mention some literature work on machine translation. And so the problem of machine translation can roughly be regarded as a problem of deciphering a sentence from one language to the others. So for example, one famous guy might be said that when we look at an article in Russian, and we say that, oh, this is actually written in English, but it's encoded in some strange symbols. And now my job for machine translation is to decode these articles into its original language. So let's see an example of some application for machine translation. For example, if we open a website in two languages side by side, we can see that by comparing the phrase or the sentence in the website, we can try to find their corresponding translation in the other language on the left-hand side. So here is usually what we want to do. We want to get the correct translation of the words in one language to the other language. So we have a lot of exciting application. For example, we can translate the Bible books, and as far as we know, that Bible is written in many languages and is widely available. So this kind of resource is actually valuable to train the machine translation system. And also we have some novels or fictions that is written in multiple languages, and which is also very popular and very widely available in many different languages. So this comes to the concept of what kinds of data we need for machine translation. So usually we are given a corpus of sentence pairs in two different languages. So we can use this sentence pair to train our machine translation models. And usually the source language is core following language and denoted as F here. And conventionally, we also use the English as the target language, but this is not restricted to English only. For machine translation, we can use many other languages as our target language nowadays. And let's see a simple example here. For example, when we look at a menu, we can see that there is usually there is some translation on the menus. And if we see this sentence, for example, these phrases, and we see some of the characters appears in most of the entries here, and we know that these identical characters would correspond to some of the words in English here on the right-hand side. And so based on this observation, without knowing any language in Chinese, can you guess which words, what does this word mean? Can anyone guess? So, so we know that this word appear frequently in in all of these entries by comparing those terms, translations. Sorry? Yeah, soup. That's correct. So I know this is might be a little bit difficult to interact on the room, but if someone can also talk to me and ask any questions during my presentation, and that would be great. And so yes, exactly. This Chinese characters can be translated to soup here in the English based on the frequency. And this is some basic idea when we're trying to learn a phrase-based or lexicon-based machine translation system. And there are some other applications, like when we're trying to decode some Asian words, or trying to find some Asian articles, and how can we know what happens or what they describe in their languages. So let's assume that when we're trying to learn the NT model in real life, there are two persons, and one is speaking, for example, the other foreign language, and the others, the listener, is trying to get some idea of what the meaning of the foreign language. So here, basically, from the listener point of view, we observe some foreign language, and we want to model the conditional probability of the correct English translation given what we observe as the foreign language. So here is F denotes the confusing foreign sentence, and E here denotes a possible English translation. So the main task for machine translation is trying to model this conditional probability. And let's assume that when the speaker trying to speak a foreign language, there is a process in his mind. For example, he wants to speak a foreign sentence. He first would trying to sample an English sentence from his mind, and then this English sentence is drawn from a probability model. And once he gets some English sentence in his mind, and the bilingual speaker will trying to use his foreign language to speak to the listener. And what the listener hears is a foreign sentence, and from the listener point of view, he would like to decode this foreign sentence to recover the original English sentence in the speaker's mind. So the decoding process here, denoted with a dashed line here, is what we call machine translation. So let's get a more detailed look at the equation here. So when we're trying to model this conditional probability of the possible English translation given the observed foreign language, we can decompose this function or this formula as several components. First, we can use the Bayes rule to decompose it to P of E times P of F given E divided by P of F here. And we know that when we're trying to pick the most possible English translation, the formula here is, or the optimization problems here is in related to the foreign sentence P of F here. So we can drop the denominators term. And now we focus on the two terms here. So P of E is actually what we call a language model, and P of F given E is what we call the translation model. And I would also go back to remind you here. So we actually want to model from the speaker's perspective. For example, we want to estimate the language model for the sentence he sampled from his mic. And we also want to model the translation model, what he used to translate the English sentence to foreign sentence. So here we have this optimization problems, and we can dive into more details later on. As I mentioned, so the language model is trying to measure how fluent or how grammatically correct for the English sentence E here. And we can use any kinds of language model, for example, an n-gram language model or a neural language model. And at the time for the statistical machine translation, we usually use n-gram language model because of its simplicity. And for the neural translation model, for the translation models here, we actually reverse the translation probability. So record that we want to model the conditional probability P of E given F. And actually we decompose into this two parts, and we want to instead model this P of F given E. The reason why we want to do that is because when we have an actual language model here, we can actually use language model to, because we have a large amount of monolingual data in English, we can train a pretty good language model. And this language model can help us to screen out or filter out some language that are grammatically wrong or non-fluent. So by decompose this conditional probability into these two parts, actually we can leverage more monolingual data in English. I think I should pause here a little bit and ask a few more questions. Is there any questions here? Okay, now let's move on. So we know that language model is pretty good. For example, when we're trying to decode a sentence in English, we can use the language model to quantify how frequent this English sentence is. But we also know that without any constraint on the source sentence, the language model can just give a very high score to some fluent sentence, but those sentence is actually not related to the source foreign sentence at all. So we need to focus on the translation model as well. And here, the translation model P of F given E, just trying to estimate the conditional probability of translating an English sentence into a foreign sentence, F here. So here is some example. For example, we are given a foreign sentence, and we have 3 possible translations. And the first 2 translations are correct translations, and the third one is clearly wrong. And we know that what we want to obtain from the translation model here is that we want to give a high score to these first 2 correct translations. And we want to give a very low score to these wrong translations. And So there is a question. When we trying to train the translation model, what kinds of parameters we can use, and how can we model this conditional probability? So notice that we are given some parallel sentence, and we know that those sentence, the frequency of those sentence in the training corpus, so that we can actually count the number of times English sentence appears in this training corpus, and also counts the number of times this English sentence and foreign sentence appears in the training corpus. And this kind of estimation is what we call the maximum likelihood estimation, which is totally based on the frequency estimation. And this is also similar to the very first example we have in this lecture. We're trying to estimate the translation frequency of soup in English. But there is some problems for this kinds of estimation. For example, we have lots of possible sentences on the Earth, and so the number of possible sentences might be close to infinite. And when we trying to count the number of sentences in our training data, which is really limited numbers, and we might not have a very accurate estimation of these formulas, and it's actually hard to generalize to some new sentences if the new sentence doesn't exist in our training corpus. So in the literature, we were trying to break this sentence translation or sentence estimation into small pieces. So this is what we call the lexicon translation. So here we want to break the sentence translation into a small pieces of lexicon translation or word translation. For example, here when we're trying to translate a German word house, we can look it up in the dictionary, and we can find there are 4 possible translations, which are house, home, shell, and household. And so we know that based on the different contexts or different scenario, we have different sense for the words, and we might have different inflections or morphologies. So a single word can be translated into different possible English words. And we also notice that some of the translations are more frequent or more common than the others. So we know that house or home or building are some common translation for the German word house. And shell is occasionally translated for house. For example, in this sentence, the house of a snail is shell. So we know that among all these possible translations, some of the English words are more frequent and some of the translations are rare. So how can we quantify those, how common is each translation? So we can basically count how many times the words is translated to the English words here. So for example, based on the corpus, we can count how many times the German word house is translated to house and translated to home. And based on the frequency estimation or the maximum likelihood estimation, we can get the total number of translation for the German word house by summing up this column, and then use the entries in each rows here as our numerator and the total sum as the denominator. So we can actually have a maximum likelihood estimation here. So here, now we break the sentence translation into the word translation or the lexicon translation here. And how can we combine them together? So here, let's assume that our sentence consists, our English sentence consists of M English words here. And our observed foreign sentence consists of N foreign words here. And we want to estimate the probability of P of E given F and M. So here we have an actual variable M here. M refers to the length of the possible translation. So let's assume that we are given the translation, the length of the translation M here, or during the training time, actually we are given the sentence pair E and F. So during the training time, we actually have the exact number of M here. But during the test time, we can usually estimate the number of the possible translation based on the length of the observed foreign sentence F here. So here, let's assume that we are given the number of the possible translation M here. So for the lexicon translation, we make several assumptions. The first assumption is that the English translation words EI in the possible translation E is generated from exactly one foreign words in F. And the second assumption here is that we assume we are given a latent alignment vector A. And AI indicates that which words EI comes from. So for example, actually in this case, AI is actually the index of the foreign words in F. And these foreign words actually is the corresponding translation for the word EI. And the third assumption here is that given the alignment A, our translation decisions are conditionally independent of each other and depend only on the aligned source words. And let's maybe take a look at this formula here. So we break this conditional probability into two parts. The first part here, we assume that we are we have an alignment probability model. So given the foreign sentence and the number of possible English translation words, we can predict an alignment vector A. And this alignment vector is actually taking from the value of n. So that basically says that A is an m-dimensional latent vector with each of its elements in the range of 0 to n. So we can marginalize over this probability to get the conditional translation probability here. So let's assume that we have an alignment probability model that can try to estimate how likely this alignment vector is. And the second part here is actually the lexicon translation, which is the probability of the English words given is corresponding foreign words here. So we already know that based on the frequency estimation or the MLE estimation, we can pretty sure to make a good estimation of this conditional probability or lexicon probability if we have a good alignment. If we can find the correct translation, if we can find the correct corresponding foreign words, we can actually have a pretty good translation probability here. Now the problem is that how can we estimate the first term, which is the alignment probability model here? So I would say that most of the research effort for the first decade of statistical MT was focused on the alignment models. So word translation, as we observe here, is easy. We can use maximum likelihood or frequency-based estimations to estimate this second term. But the first term here is more difficult. We want to make sure that the word order is correctly predicted. So I probably will pause here, and is there any questions? Okay, so let's continue. Here, so let's give an example of what word alignment is. So word alignments can be visualized by drawing some lines between words in English and words in the foreign language. So for example, we notice that this is the English words, English sentence, and we have 4 English words. So the number of elements in the alignment vector would be 4. And we know that this is a one-to-one alignment. So the first English words is aligned to the first German words. And we know that the English word der come from the first German word. So we have the index 1 here for these German words. And the house comes from the second word house. So we have 2 here, and so on and so forth. And let's take a look at the some reordered case. For example, we know that, for example, der comes from the third German words, das here. And we know that the latent vector, the first elements of latent vector is 3, which is the index of the foreign words here. And house is aligned to the fourth German words, house here. So the second element is 4. Notice that here, the alignment vector is the index of the source of the foreign sentences. And we also know that some of the source words, for example, some of the source word does might not be translated at all. So we were missed the index of does in the alignment vector here. So in this case, the possible translation only consists of 3 English words. So we have 3 elements in this latent vector A. And also, we know that some of the English translations might have some extra words that is aligned to none of the words in the source sentence. So we would like to create a pseudo tokens here called null, and we would like to align these actual words to this null token. So here we create the index 0 for this null token, and then for this alignment vector, we have 0 for the word just here. And also we know that some of the source word might translate to more than one target word. For example, this word is translated into 2 English words, for example, very small here in this case. And so we know that very also comes from the fourth source word, and small also comes from the fourth source word. So here we have 2, 4 here in this alignment vector. But there is a problem if we have one target translation words and it actually comes from 2 source words. So how can we represent the latent alignment vectors here? So can we represent it as the tuples here? So this would give some trouble for the later on computation. So when we encounter these problems, we introduce the phrase-based translation. So basically, in this case, we use the word as the processing unit, but in phrase-based translation, we use the phrase as the processing unit. So here in this case, we would group these two words together and regard it as just one token. And I will talk about the phrase-based translation later on in the slides. And let's now focus on the lexicon translation or the word-based translation here. So I will also introduce one popular alignment-based model, which is the IBM Model 1. And it's very simple, and it also has some additional assumptions. For example, here, the first assumption is that the alignment decisions are independent, which means that the alignment of words cannot affect the others. And the second assumption is that the alignment distribution for every word's AI is uniform over all the source words and the non-token. This means that we have this formulas to construct the latent alignment vector here. For every predicted English words, we're trying to sample the alignment words from the range of the target words. So notice that here, the alignment vector have the same length as the target English sentence. And each element in this alignment vector correspond to the index of the source word that this English word comes from. So here, this model basically says that, hey, for every alignment element, I just randomly draw words from the source word, from the target, from the source word, yes. And then based on the alignment words, I would trying to use our translation model to predict a possible English words. And here is an example. For example, let's say I randomly draw the alignment, and the alignment is here, 1 to 1 and 2 to 2, and so on and so forth. And then we can, based on the alignment, conditional on the foreign words, we can predict one English words one by one. And after we predict the English words, we can use the language model to give a score. And the language model says that, yeah, this is a pretty smooth and fluent sentence. But if we randomly draw some alignment, there might be some case that the alignment might be wrong. So based on the wrong alignments, even though we can have a better, very good lexicon-based translation, we actually mix the order. Then the language model would say that this is not a smooth or fluent sentence. So we here face problems. When we're trying to learn the parameter P of E given F on the parallel datas, F and E, we actually have some chicken and egg problem. For example, if we have a very good alignment model, we can actually estimate the translation probability very well, because we can, for example, use the maximum likelihood estimation to count how many times those aligned words coexist in the training corpus, and then we can compute their translation probability. The second issue is that if we have this translation probability, we can actually use the greedy algorithm. For example, every time pick the most likely, the words with the most likely translation probability as our alignment, and use those those probability, we can actually predict the alignment for every words in the source sentence and in the target sentence. So we actually cannot figure this out at the same time. So what's usually, what kinds of algorithms should we have here? So I will pause here and then give you guys some sorts, and can anyone trying to answer what kinds of algorithms can we use to solve this chicken and egg problem?
Something like expectation maximization.
Yeah, that's correct. That's exactly. So for expectation maximization algorithm, we actually want to iteratively learn the translation model and the alignment model at the same time. So the algorithm goes on like this. At first, we just randomly pick a starting alignment. For example, we can have the random alignment or uniform alignments here. And then we go through a for loop. For the for loop here, we can, based on the alignment, we can compute the alignment probability here. And then we can count how many times those foreign words are translated to the English words based throughout all the corpus. And then we can have a better estimation of the translation probability based on the maximum likelihood estimation. And then we can use this frequency estimation in the MLE equation to get the good parameter. And afterwards, I can try to use this parameter to estimate a better alignment probability. So to estimate those alignment probability, for example, every time when I trying to predict the alignment between the source word and target words, I trying to compute the conditional translation probability over all the possible English words, and then I pick over all the foreign words, and then I pick the highest one as my alignment prediction. And then we iterate this process until we reach some conversion conditions. So here's an example. Let's say first we assume that all the alignments are equal between these parallel sentences. And we found that in the first iteration, we found that there is usually aligned to lar here. So we know that this alignment is frequent. And then after one iteration, we know that this alignment between lar and the are most likely. Then we can just, for example, prune up some of the link with lower probability. For example, Martian is aligned to brew only once, while Martian is aligned to house twice. So we prune up some of the low frequency link here. And we know that flower is actually aligned to floor here because of the pigeonhole principles. And then we can iterate this process again. Then we can get the correct alignment from these iterations. And then later on, we can use this correct alignment or this estimate alignment to have a better estimation of the lexicon translation here based on the maximum likelihood estimation. And we can try to see this table. So let's assume that at the very beginning, each word is translated to the target word equally. So after 1 and 2 iterations, we can find that the translation probability might change. And then after a few iterations, those translation probability would just converge. and then we can get the correct alignment. So far, is it clear? I will pause here for some questions. Okay, let's move on. So based on the lexicon or word-based translation models, I mentioned that we can actually extend this model to phrase-based translation. So here, basically, we group some of the words or frequent n-grams together as one processing unit. And we can use the exact same model or procedures as the lexicon translation to do this phrase-based translation. And the other extension is word alignment matrix. So we can post some priors on the alignment matrix here. For example, for IBM Model 1, we assume that the initial alignment is uniform among all the possible source words. And here we can have some human priors that assumes the alignment decisions are not uniform. They basically have diagonal patterns. For example, the first word where the first source word is aligned to the first target word, and the second source word is aligned to the second one, and so on and so forth. So we can have some alignment probability for the alignment model, and we can start from this initial point to do our EM iteration. And the other extension would be leveraging the syntactic tree structure. For example, we know that their language actually can be passed into some syntactic tree. And we know that those tree structure actually have some similar pattern among several languages. For example, in this Chinese sentence, we know that the word 之一 x 之一 is actually similar to the sentence one of the trees here. So we know that x 之一 can be translated to one of the x most of the time in English. So we know this rule, and we can deduce actually from this syntactic trees. And if we can deduce those rules from these syntactic trees, we can actually leverage those rules to generalize to some unseen sentences. For example, X can be any nouns in Chinese. And we know that use this rule, we can actually translate it into one of the X, and where X is the target word in English. And now let's move on to how can we evaluate the MT system. So
I have a question.
Okay.
For the EM algorithm, what's like the time complexity of that?
This is a good question. So for EM algorithm here, actually every time it depends on the number of iteration. Usually we have a fixed number for the iteration here, and inside this for loop, actually what we need to do is two things. One is that we need to recalculate the translation probability. So this will go through the whole corpus. So this process actually is related to number of sentences in the parallel corpus. And estimate the alignment is pretty easy. So I would say roughly this time complexity would be O times number of iteration times O number of iteration times number of corpus, number of sentences in the corpus. Is it clear?
Yeah, thank you.
Okay, yeah, so yeah, let's move on to the evaluation. So the central idea for how to evaluate a possible translation is we want to compare our output from our MT system to a human or professional translator's output. And this is this matrix is called BRU, which is what we commonly use in evaluate MT system. BRU score is actually the geometric mean of the n-gram precision against the human translation plus lens penalty term. I will talk about this formulation in more details in the following slides. Before that, let's look at a concrete example. For example, our MT system output the candidate sentence like here, and then we have 3 human reference sentence. And we notice that when we trying to compute the n-gram precisions, we actually compare the sentence word by word here, and the words in red highlights the words overlap with the words in the reference. And we notice that, for example, here, this word, in this predictions, we have 17 words that are covered by the human reference, and we only miss 1 word in our prediction. So the unigram precision would be 7 divided by 18 here. And clearly we can observe that there are some issue for this n-gram precision. For example, if we have a very trivial prediction, like we have all the word be a single identical word the, and the actually is covered by one of the words in the reference, and we have 7 divided by 7. Then we have a pretty high score for this unigram or this n-gram, this unigram precision. And the solution here is that we can only match 1 word, and then we will just delete this word from the reference, and then all the reference words that match with some of the words in the prediction would be exhausted after it is matched. And in that case, for example, we have, let's say we have 3 words there here, and these 3 words would be matched, and then they will be exhausted, and then we won't have a 7 here in the numerators. And the other issue of this BRU score is that, for example, if we predict a sentence which is really short and it only consists of 1 word, if these words match any of the words in the reference, we will also have 1 divided by 1, and this is pretty high. So the solution to address this issue is to add the lens penalty, which will penalize the candidate if it is too short. So here is the formula for the BRU score. So it consists of geometric mean of the n-gram precision from unigram to 4th gram, and another lens penalty terms. Basically, this lens penalty terms is that if the sentence is shorter than the reference sentence, then this term will smaller than 1. And if the sentence is too short, then this term will decrease and goes to 0. So we usually have this. So this BRU score is from 0 to 1, and usually when we show the BRU score in the paper, we usually multiply it by 100. And usually 1 BRU score is pretty significant gain. And some very popular MT system can get some score between 10 to 30. And the human translator can usually get some score between 70 and 80. And yeah, so let's, before I move on, is there any questions? Okay, now let's move on. So from now, I mainly cover some of the related work on word-based or phrase-based MT system. Now let's move on to neural models. And we know that since 2014, most of the research on MT just shift to neural models. And surprisingly, we found that neural models are simple and they are actually very effective if we have larger numbers of training sentences. So let's talk about some basic concept about neural models. The first concept is neurons. So we know that for neural network, we were trying to represent a sentence by some vector representations. Let's say we have some input X here, and it consists of some elements in a vector. And we're trying to have a weighted sum over these elements to get the new neurons, Y here. And we also want to have non-linear activation functions of the aggregation functions here. So we have we have the output. We also add the nonlinearity in the neural model, just trying to increase the representative powers of the neural models. And for some nonlinear function, we usually use some sigmoid or red rule functions. And we can have multiple neurons in the output layers. For example, we can have the weight matrix to get a vector's output Y here. So this Y consists of 3 values or 3 scalars, and it's a 3-dimensional vector. And we can also add the nonlinearity over the aggregation functions here, the weighted sum here. And for some basic sentence classification or classification tasks, we can add, for example, a softmax function over this predictive value Y here to, for example, have a 3-class classification prediction. And we can also add more layers on top by, for example, adding another vector, weight matrix V here, and we can have another layer outputs. And so on and so forth. We can also, like, for example, if we don't have any, if we don't have any nonlinearity here, we can actually write this as a single vector, single weight matrix U for these 2 weight matrices. So we know that if we have more nonlinearity function here, we can actually increase the representation powers of the neural network. And we also have some complicated structure like recurrent neural network, where the current prediction where depends on not only the source input X, but also its previous input Y1, for example, here. And there's some decision when we're trying to design the neural MT models. There is, for example, there are some popular questions like how many layers do we need to train the model, how many neurons, or what kind of structure, recurrent neural network or transformer-based structure, and what kinds of activation function I need to use. And later on, I will try to briefly mention some choice in the popular models. Let's take a look at the, for example, representation in neural models. So at the very beginning, we know that we can use bag of words to represent a single word. For example, we can use 0, 1, a one-hop vector to denote the word dog here based on the, and this vector has the same size as the word vocabulary. But this is not efficient for this kind of representation. So later on, people introduced the distributed representation, which is also called the word embedding. So the word embedding is a low dimensional vector which usually consists of 300 dimensions, and to represent one word. And this word vector actually can represent a single word in the word embedding space. And we can learn those words by some popular method like skipgram. And for the neural model, it's actually supervised model. So we actually are given a set of, for example, sentence pairs, and we will go through this process. For example, we will give the sentence pair to the network and ask the network to predict a y for this input x. And then we compute the loss, the sequence loss y with the ground truth y star. And then we use backpropagation to compute the gradient and backprop the gradient through the network to update the parameters. And some of the popular neural language model are actually proposed quite a while ago. For example, Bengio actually proposed a neural n-gram language model. Basically here, we have, for example, when we're trying to predict the ice word, we are actually conditional this prediction on the last n words. So this is an n-gram language model. And we can, for example, have this kinds of architecture for our prediction. First, we have one hot vector for this E, and we go through a word embedding matrix, so we can have a low dimensional word vector here. And then, for example, in this case, we have the trigram language model. When we're trying to predict the ice word, we condition our prediction on the previous 3 words, and then we can encode these 3 words using the feedforward neural network, as I mentioned before, and then we can have the conditional probability here, and use a softmax. We can try to predict the probability of the word based on the inputs. And this vector is actually has the elements of number with the same elements of number of words in the vocabulary. And here, Bengio also has some experiment in their papers, like, for example, if you increase the number of layers in the feedforward neural network, and you also increase the some of the n-gram m to 5, and you can actually see a pretty low perplexity score, which is better than the language model, the n-gram language model here. So let's note that this n-gram language model is actually a unconditional language model, while you can regard the translation model as the conditional translation model, where we want to predict the translation probability P of E given F rather than P of E here for in the neural language model case. So for the conditional language model, what we want to do is that we want to give the previous n English word that we generate to the decoder, and we also want to give the aligned source word as some information to our decoder. So here, one basic idea is that we can, for example, one very simple baseline is that we can concatenate the aligned words FAI here together with our previous n English words, and then we can try to predict our English words EI here. So the conditional translation model, we can just approximate this probability as this formulation. So basically means that our prediction depends on the previous English words and also the aligned source words. And we also have windows between the aligned source words. We're trying to integrate the information within a window. And we can use a very similar architecture, for example, a feed-forward neural network to decode one source word here, one target words here. And this actually performed really well. For example, if we have if we increase the windows of the source words, we have increased BRUTE score. If we have more layer or more parameters in the feed-forward neural network, we can also observe some gain. If we increase the vocabulary or add some non-linearity function, we can also observe some gain from that. So let me simplify the notation for the neural network. I was trying to use the rectangle to represent the circles here. So I will also talk about, so previously we talked about feed-forward based neural translation model. And I will talk about the recurrent neural network model, where for recurrent neural network, our prediction not only based on the source information, but also based on the previous information. So you can see that in each cell of the recurrent neural network, we have two kinds of input. One is the input from the source sentence. One is the previous hidden vectors. So this is for this neural MT models, we usually use the concept called encoder-decoder models, where we have the encoder trying to encode the information from the source sentence, and we also have the decoder where we want to use it to decode the target sentence or target word one by one. So the attention, so we know that for this kind of encoder-decoder model, there is clearly a problem for long sequences, because the recurrent neural network is trying to compress arbitrarily long sentence into a finite vector, finite length word vector. So if we want to look up some of the source word when we're trying to generate one particular output words, what can we do? There is another work trying to introduce the attention mechanisms. The intuition is very simple. It's also actually very similar to word alignment, as we mentioned. So when we're trying to generate, for example, an English translation based on this Japanese source sentence, we would refer to some of the particular words in the Japanese sentence when we're trying to generate these words. And then we go on one by one. Then we can actually find the correct translation for a particular source word. So based on this intuition, how can we compute this attention mechanism? Here is what we do. For example, when we're trying to decode this word, this target word at the t time step, we're trying to use this word vector as the query vector and use the hidden vector of the source word as the key and the value. So we use the query to compute the similarity between all the key vectors or all the word vectors here. And then we can have some similarity measures here, similarity scalar here. And then we use this similarity scalars as the way to aggregate the information from all this word vector. So we basically perform a weighted sum over this word vectors, and then we get a single vector, which is the context vector. And later on, we get these context vectors we would use the contact vector together with the hidden vector here to predict the word. So notice that here is what we trying to use attention method to summarize some key information for some key information from the source sentence given the time step here. And the time step information, the information at this time step will also be very useful for us to predict one word. And then we later on pass the hidden representation to the next step, and then we can fit the predicted tokens to the neural network to get another query vector. And then we perform another attention mechanisms, and then we can try to get the second word. And we go on until we reach the end of sentence token. Is it clear? Okay. So for the other research, we also want to know that some people would also use convolution neural network to encode the sentence. Here in the previous slides, we use recurrent neural network for both the encoder and decoder. But in this paper, Facebook also explored some new architecture or some architecture like convolution neural network to encode the sentence. Basically, they will also encode the words within a fixed size window, and then trying to do attention as well. And they, in this work, they also use the recurrent neural network to decode the sentence. So there is another work which is also impactful for neural machine translation, which is the transformer model. So we know that use the IM model to encode the source sentence is not very efficient because you want to encode the sentence from left side to right. While for GPU, actually, we want to compute the word embedding in parallel. So this is done by self-attention. Well, for self-attention here, instead of encode the sentence from left to right, we actually have a self-attention over, we have multiple layers of, in the attention models, in the self-attention encoders here. Between each layers, we can actually have a weighted sum over the word embedding in the lower layers, and then we can generate a new hidden representation. So we go on here. So this encoding is actually independent of the previous vectors. So we can actually compute this self-attention in parallel in the GPU. But we also know that in this case, we actually miss the ordering information. So for the transformer models, actually for every input, we have a position embeddings here, which I didn't write it here. So the position embedding actually is trying to distinguish words based on their positions. For example, they actually have a lookup embedding tables, and then they can compute the word in the position embedding for the first words in the source sentence, and compute the second word, the position embedding for the second words. So and this is self-attention encoders, and for the decoder, actually they also use the cross attention, as I mentioned here, use one of the words, one of the target word hidden representation as the query, and use the source word hidden representation as the key and value, and use the query to attend to the key and value and perform a weighted sum over the value vector, and then get the context vector. Then they can predict the target word one by one. So yes, I think I can skip this one. So for self-attention, we can actually find some interesting pattern. For example, some attention weight can actually help us to detect some long-term dependency. For example, matching can between layer, this is the upper layer and this is the lower layer. And notice that we want to perform self-attention to the lower layer key and values. And we can actually visualize the attention weight. And then we can find that when we're trying to encode the word making in a higher layer, we're actually trying to aggregate information from making and more difficult here. So which makes sense when we're trying to encode the more abstract meaning of making. And transformer model becomes very popular nowadays, and then we can use more efficient ways to train such big models and obtain very significant improvement over some previous neural models. And finally, I will try to briefly mention some of the key direction or research direction in neural machine translation. So we have more powerful computational models like transformers, but we also want to incorporate some of the syntax in the neural models. So I know that some of the paper trying to leverage some tree structure, as we mentioned in the phrase-based machine translation model, trying to incorporate those informations to the neural models. And the other research direction would be trying to handle some morphologically rich languages. For example, how can we deal with language that has multiple morphologic forms? So some basic solution, for example, would be develop the subword unit representations. And the others would be how can we optimize the translation quality? And some of the research also introduce some concept like dual translation, where you want to train two translation model, one to translate the language forward and one translate the language backward. And you also want to maintain the translation consistency. And the other very hot topic is multilingual models, where you want to transfer the knowledge you learn from one language to the other language, because we know that some of the words actually share among different languages, and we can transfer those information. And the other research direction would be document level translation, where here we focus mostly on the sentence level translation. We also want to get the document level information to keep the sentence more coherent. And basically, that's all. Is there any questions? Yeah, I will leave here for a few moments to answer questions. If you have any questions, I'm happy to take. Okay, now, so if you have any more questions, feel free to send the email to me, and I'm happy to have an interaction with you through emails.
Sorry, can I ask a question?
Yeah, sure.
So I was wondering if machine translation sometimes is relied on like language detection, because I know a lot of, because if you're given a text, you want to translate it, then you first want to know which language it is and which language do you want to translate to. So is machine translation relied on language detection?
Yeah, this is a good question. So when we comes to commercial system, we first trying to, so for example, Google Translate, when you post a sentence to Google Translate, first it will trying to detect what kind of language you are asking. And then they were internally use a toolkit called CLD2 or CLD3 currently they are using. And later on, they were based on the predicted language and use the correct model to predict, to translate your source input to a target language. And this is also related to multilingual models. So you can clearly see that there is some limitation for this method. For example, user or the Google need to train multiple systems for multiple language translation pairs. While here for multilingual models, their target is that we want to train a single model to handle multiple, the input from multiple languages. For example, in this case, if we use a multilingual models, no matter what kinds of inputs in what kinds of language you are asking, I can directly throw this input to a multilingual model and then decode one sentence in English or whatever target languages.
Okay, so does that mean you can encode any text in any language into one single representation?
That's correct for in the multilingual models.
Okay, wow, thank you.
Yeah. Any questions?
All right, let's give a round of applause for our guest speaker, Junjie.
Thanks.
And thank him. Junjie, are you going to post the video, or?
I'm fine. Yeah.
You made a recording, right?
Yeah, I made the recording.
Okay. Can you get that to us so we can?
Yeah, sure.
We can post it.
Yeah.
Okay.
Sure.
All right. Thank you very much.
Yeah. Thanks. Bye.
Goodbye, everyone.